Okay, we're moving on to section 12.4, heat engines and the second law of thermodynamics. Let's bring up the PowerPoint. Okay. A heat engine takes in energy by heat and partially converts it to other forms, for example, electrical and mechanical energy. In a typical process for producing electricity in a power plant, for instance, coal or some other fuel is burned, and the resulting internal energy is used to convert water to steam. The steam is then directed at the blades of a turbine, setting it rotating. Finally, the mechanical energy associated with this rotation is used to drive an electric generator. In another heat engine, the internal combustion engine in an automobile, energy enters the energy as fuel is injected into the cylinder and combusted, and a fraction of this energy is converted to mechanical energy. In general, a heat engine carries some working substance through a cyclic process during which, number one, energy is transferred by heat from a source at a high temperature, work is done by the engine, and finally, energy is expelled from the engine by heat to a source at lower temperature. Let's think about the operation of a steam engine in which the working substance is water. The water in the engine is carried through a cycle in which it first evaporates into steam in a boiler and then expands against a piston. After the steam is condensed with cooling water, it returns to the boiler and the process is repeated. It's useful to draw a heat engine schematically as shown in the figure. The engine absorbs energy QH from the hot reservoir, does work WENG, then gives up energy QC to the cold reservoir. Note that negative work is done on the engine so that W equals minus WENG. Because the working substance goes through a cycle, always returning to its initial thermodynamic state, its initial and final internal energies are equal, so delta U equals 0. From the first law of thermodynamics, we can write these equations. The second equation shows that work, WENG, done by a heat engine equals the net energy absorbed by the engine. From the figure, we can write this equation shown here. Generally, a transfer of thermal energy Q can be either positive or negative, so the use of absolute value signs makes the signs of QH and QC explicit. Q net equals absolute value of QH minus Q cold. Q hot, absolute value of Q hot minus absolute value of Q cold. Okay. If the working substance is a gas, then the work done by the engine for a cyclic process is the area enclosed by the curve representing the process on a PV diagram. This area is shown for an arbitrary cyclic process in the figure. The thermal efficiency, E, of a heat engine is defined as the work done by the engine, WENG, divided by the energy absorbed during one cycle. We can think of thermal efficiency as the ratio of the benefit received, that is the work, to the cost incurred, energy transfer at the higher temperature. This equation shows that a heat engine has 100% efficiency, that is E equals 1, only if QC equals 0, meaning no energy is expelled to the cold reservoir. In other words, a heat engine with perfect efficiency would have to use all the input energy for doing mechanical work. That is impossible, as we'll soon see. Refrigerators and heat pumps. Heat engines can operate in reverse. In this case, energy is injected into the engine, modeled as work W in the figure, which results in energy being extracted from the cold reservoir and transferred to the hot reservoir. The system now operates as a heat pump. A common example of a heat pump is a refrigerator, as shown in the figure. Energy Q is extracted from the interior of the refrigerator and delivered as energy QH to the warmer air in the kitchen. The work is done in the compressor unit of the refrigerator, compressing a refrigerant such as Freon, causing its temperature to increase. A household air conditioner is another example of a heat pump. Some homes are both heated and cooled by heat pumps. In winter, the heat pump extracts energy QC from the cool outside air and delivers energy QH to the warmer air inside. In summer, energy QC is removed from the cool inside air, while energy QH is ejected to the warm air outside. For a refrigerator or an air conditioner, a heat pump operated in cooling mode, the work W is what you pay for in terms of electrical energy running the compressor, whereas QC is the desired benefit. The most efficient refrigerator or air conditioner is one that removes the greatest amount of energy from the cold reservoir in exchange for the least amount of work. The coefficient of performance, COP, coefficient of performance for a refrigerator or an air conditioner is the magnitude of the energy extracted from the cold reservoir divided by the work performed by the device. The larger this ratio, the better the performance, because more energy is being removed for a given amount of work. A good refrigerator or air conditioner will have a coefficient of performance of 5 or 6. A heat pump operating in heating mode warms the inside of a house in winter by extracting energy from the colder outdoor air. This statement may seem paradoxical, but recall that this process is equivalent to a refrigerator removing energy from its interior and ejecting it into the kitchen. The coefficient of performance of a heat pump operating in the heating mode is the magnitude of the energy rejected to the hot reservoir divided by the work done by the pump. In effect, the coefficient of performance of a heat pump in the heating mode is the ratio of what you gain, energy delivered to the interior of your home, to what you give, work input. Typical values for this COP are greater than 1 because the magnitude of QH is usually greater than W. In a groundwater heat pump, energy is extracted in the winter from water deep in the ground rather than from the outside air, while energy is delivered to that water in the summer. This strategy increases the year-round efficiency of the heating and cooling unit because the groundwater is at a higher temperature than the air in winter and at a cooler temperature than the air in summer. Okay. The second law of thermodynamics. And I think we'll stop here and we'll pick up the second law of thermodynamics in the next video. These things can get too long if we keep going and going.